Okay, thank you very much. Uh, First of all, I would like to thank the organizers, including Professor Sharif, and I would like to celebrate the birthday of Professor Kadir, 75 years old. Thank you very much for everything. Today, I'd like to talk about a review on the issue of dark energy and modified gravity. This is the collaboration based on the collaboration with Professor Dr. Joseph and Dr. Bati. Uh, they, uh, they have been supporting our very nice conference, and especially to me, they uh, helped me very, very much. So I'd like to thank Professor Dr. Joseph and Dr. Bati. In this presentation, in the first part, I would like to review the dark energy problem and the modified gravity theories. And then the second part, as an example of our recent work on the modified gravity theories, I'd like to talk about the dynamical system analysis of Planck type 1 spacetimes in F of R gravity. In the first part, already Professor the Paulus has explained the current expansion of the universe is accelerating. This is called the dark energy problem. This is a supernova legacy survey data. The horizontal axis showed the redshift and the vertical axis showed distance estimators. We can see that the flat lambda cosmology can fit data better than the pure matter cosmology. This is a baryon acoustic oscillation data. The horizontal axis shows the separation of the convection scales, and the vertical axis shows the two-point correlation functions. This is a baryon acoustic oscillation for the large-scale structures. By combining the supernovae, BAO, and the cosmic microwave background radiation, we can see that we have the information of the fraction of dark energy and the fraction of dark matter here. From this figure, we can see that the current three cosmic compositions are as follows. The dark energy is about 70%, and the dark matter is about 25%. The other matter, namely the baryon, is only 5%. This means that if the current cosmic acceleration is realized, then the dark energy with negative pressure, the strength of the negative pressure is stronger than the ordinary universal gravitations. There are two main approaches to explain the issue of dark energy. The first is the relativistic approach, namely, we introduce the dark energy with its negative pressure. Dark energy is unknown even now. The second is to extend the gravitational theories in large scales. This is the gravitational field equations. The first approach is to add some unknown energy components called dark energy on the right-hand side here, matter component. The second is to extend the gravitational sector on the left-hand side. The condition for the accelerated expansion of the universe is as follows. Suppose the metric is given by the homogeneous and isotropic one. The equation of the scale factor for a single phase is given by these expressions. The accelerated expansion is realized when the A2 dot is positive, namely the equation of state W, the P over rho. Here, P is a pressure and rho is an energy density, should be less than -1 or over third. The current Planck data for the W is given by this, namely the less than -1 over third. That's why the current expansion of the universe is accelerating. I would like to explain several approaches, several proposals for the general relativistic approach. The first is the cosmological constant. Second is the scalar field, like X matter quintessence. Moreover, there are several candidates for the dark energy: phantom with wrong sign kinetic term, K-essence with non-canonical kinetic term, tachyon predicted by string theories. The third is a cosmic fluid. For example, the Chaplin gas, whose equation of state is given by this peculiar form. The pressure times energy density is constant. And the viscous fluid is also proposed. Next, I would like to explain the several proposals of the extension of gravitational theories. The first, the most simple one is F over gravity, which is explained in detail in the second part. The second is the skeleton theories, like this form, like such as the Browns-Leakey theories. Moreover, there are several candidates for the extension of gravitational waves. The Gauss condensates, higher order curvature term like Gauss-Bonnet term, and the arbitrary form of the Gauss-Bonnet term. And the DZP brain world scenario, F of T gravity. Here, T is the torsion scalar and the teleparallelism. The teleparallelism, they want to use the Weisenberg connection, which has no curvature in ordinary general relativity in Riemann geometry, but the torsion rather than the curvature defined by the Leibniz connection in general relativity. And the Galilean gravity, whose Lagrangian is given by this form. In this case, the equation of motion are invariant under the Galilean shift, and therefore the equation of motion can be kept up to the second order. This is very welcome because we can avoid the appearance of the extra degree of freedom associated with ghosts. The Horndeski theory is a kind of a generalization of Galilean gravity. Moreover, non-local gravity predicted by quantum effects, the relativistic gravity, massive gravity, and by gravity with two metrics. Here, I would like to explain F over gravity. The action is given by this expression. If F over r is exactly r, scalar curvature, this theory is recovered to general relativity. In this case, the gravitational field equation is given by this expression. In the homogeneous isotropic flat universe, the gravitational field equations are given by this expression, and therefore, the effective equation of state of the universe is given by this expression. For example, if we consider the very primitive form of the F over R, original form, like two power law forms, in this case, the scalar factor A can be explained and can be expressed by such a power law form. If the power Q is larger than unity, the accelerated expansion can be realized. For example, if n is equal to 1, namely Q is equal to 2, double effective is given by this expression. This is less than minus over 1 over third. For the exponential gravity, we can realize the evolution of the standard evolution of the energy fractions. Horizontal axis show the redshift. The vertical axis show the fraction of the energy components. We can see that the dark energy components will grow up around current universe. That's why this F-bar gravity model can produce the standard cosmology. Here is the ordinary dark matter, and the radiation is always small fractions, much smaller fractions. There are several conditions for the viable F-bar gravity models. The first is F prime is positive. This is a positivity of the effective gravitational coupling. Second is F2 prime should be larger than 0. This is stability conditions for the theory. The third is the cosmological requirements. The F-bar should be R plus cosmological constant for the scalar curvature is larger than the current curvature values. This is the existence of a matter-dominated stage. The first is this expression. This is the stability of the late-time digital point. The fifth is constraints from the vibration of the equivalence principle, namely the solar system constraints. For F-bar case, the so-called chameleon mechanism is used for this solar system constraints. And the literature, there are several concrete models are proposed. For example, Ustavitsky model, Starobinsky model, Tsujikawa model, and exponential gravity model. Okay, let me summarize the first part. In this first part, we have explained the late-time cosmic acceleration, namely the dark energy problem, and review the candidates for dark energy and the modified gravity theories. Now let me move to the second part, the dynamical system analysis of Bianchi type 1 spacetimes in F-bar gravity. This is a collaboration with Dr. Chakraborty and Professor Sar. In this work, we present a dynamical system analysis in terms of new expansion normalized variables for homogeneous and anisotropic Bianchi type 1 spacetimes in F-bar gravity under the presence of anisotropic matter. We demonstrate that the Einstein's equations are reduced to an autonomous 5-dimensional system of ordinary differential equations for new variables. We make the autonomous system analysis in vacuum for the power law form of F-bar and show that the dynamics can be solved exactly. In the literature for homogeneous and isotropic spacetimes, there are several works, and also the Kastner type vacuum solution. There are also several papers by Professor Burrows. Here we consider the F-bar actions plus the ordinary matter contributions to the total actions. The homogeneous and anisotropic Bianchi type 1 space-time metric is given by this form. Here A is an average scale factor and beta are quantities which characterize the anisotropies. We introduced these relations for beta, and therefore the sigma square is the total amount of anisotropy and the metric. And also H is average Hubble parameter. In this case, the scalar curvature is given by these expressions, and the energy momentum tensor of an anisotropic barotropic fluid is given by these expressions. And also, we introduced an isotropic equation of states here. And omega is the average barotropic parameters. In this case, we have introduced these parameterizations. And In this theory, we have the following set of field equations for H, low, beta, plus minus. Here, beta is a quantities for describing the anisotropies of the universe. The first two, 1, 2 are the ordinary Friedmann equations. The third is an equations for the anisotropy. The fourth is the ordinary continuity equations. If beta is exactly zero, namely for perfect field, we have this ordinary form of, and to analyze our system, we introduce the logarithmic time n, and we introduce the following dimensionless expansion normalized dynamical variables: U1, U2, U3, U4 plus minus, and U5. From the first equation, namely the first equation of the Friedmann equation, we have this form. This is the energy constraint. And the second to four equations, we have the five-dimensional system of autonomous first-order differential equations. These are equivalent to the second, third, and fourth equations in the previous slide. This one is our autonomous system equation set. Here, gamma is given by this expression. Gamma is depend on the form of f of r. For example, if we consider the concrete form of f of r, the gamma is given. First, the power law form, gamma is given by delta inverse. Here, excuse me, here. Delta is this power. The second is the logarithmic form. We have this form. The third is the exponential gravity. Gamma is given by this. The fourth is the prototype of f of r, like a two power law form. This one. And the third is the double power law. If A is unity and B is 2, this is the so-called Stravinsky inflations. This Stravinsky inflation is consistent with the current Planck data. This is a 2018 Planck data. The horizontal axis shows.
You have
yes.
2 minutes, please. So please conclude your talk. You have 2
minutes. Okay. I will continue. Okay. The horizontal axis shows the primordial tilt of the scalar mode of the metric perturbations, and S. The vertical axis shows the tensor to scalar ratio, R. Now we can see that here, this is the R squared inflation, namely the Stravinsky inflation. This is consistent with the Planck 2018 data. This one, R squared inflation. I would like to explain the application to cosmology. The first, we consider the very simple case, the single power law R is f of r is given by this power law form, and for simplicity, we consider the first case of vacuum, namely the new variables u5 is exactly the error. In this case, we have a two-dimensional phase space spanned by the variables u1 and u4. The autonomous system form is given by these expressions. In this case, we have this diagram. Horizontal axis shows the U1, vertical axis shows the U4. This is the U1, U4 diagram. And this line is the invariant line. We can see that 0, 0 is the fixed point, and this is stable. So this point leads to the digital stable solutions. that this form is this diagram is just for the delta is exactly unity. This means that the this diagram is for r square gravity. From this result, we can see the following points. The vacuum solutions in the case of f of r with a delta is unit delta is exactly unity. For u5 is exactly 0 are solvable exactly. For example, case of delta is equal to unity, the stable fixed point corresponds to the Dojita solution. This is the solution of Stravinsky inflations. This result is consistent with the past famous works. The point of our work is that to give the systematic way to reproduce R square gravity in a consistent way compared with the past related works given shown in here. Also, the R is given by this expression. We have these forms. Therefore, from energy constraints, we have the very simple differential equations for F. This equation have a unique solution like R squared. From this analysis, we can see that the case of R squared is unique among all vacuum F-over theories with respect to the existence of the Dojita solution with arbitrary form of H. Next, this is the case of delta is 1/10, namely the point 1. The horizontal axis showed U1 and vertical axis showed U4. This is the invariant line. We can see that we have a fixed point here. However, this is unstable fixed points. If the case of delta is not exactly unity, we have these forms, and therefore the Hubble is given by this form. In this case, if the delta is positive, we have a big wave singularity, namely the future finite time singularity. If delta is negative, then we have a power law expansion. We have also considered the power law form of f of r in the case that there exists the anisotropic matter. In this case, U5 is not exactly the arrow. And in such a case, the autonomous system set of equations are given by these expressions. In this case, we find 4 isolated fixed points, namely the following value of the pair U1, U3. As a result, we see that in the case of with the anisotropic freeze, all isotropic fixed points are unstable, namely that there is no asymptotically stable isotropic solution in the presence of anisotropic matter. Also, we have found that for the case of exponential gravity, we find the same consequences.
Can you hear me?
Okay, let me summarize the second part. In the second part, we have analyzed the cosmological solutions for homogeneous and anisotropic Bianchi type 1 spacetimes in F over gravity under the existence of anisotropic matter. It has been demonstrated that the Einstein's equations are reduced to an autonomous 5-dimensional system of ordinary differential equations for new variables we introduced here. By making the autonomous system analysis of the vacuum solutions for the parallel form of f of r, we have shown that the dynamical system can be solved exactly, and that only for the case of R squared, there exists a stable Dojita solutions, namely the solution of Stravinsky inflation, consistent with the recent Planck results. The point of our new work is that to present the systematic way of R square inflation, R square gravity, which is consistent with the past related works. Okay, let me summarize the second part of this presentation. Thank you very much.
Thank you very much. So one quick question, please. Yes, Professor Khan.
You mentioned the torsion scalar. How do you define torsion scalar?
Actually, how we can determine
Torsion scalar.
That's the definition.
R square, R square, excuse me. What we
How do you define torsion scalar?
R square. Okay.
R square. Okay, thank you very much. If you have
Okay. R square is a okay. I just I'm sorry. Please wait a moment. I would like to show the sorry. Okay. 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 The answer for your question is this one. So we have this form of the very simple equation, the differential equations. The only unique solution is given by this form, so we can obtain the R square gravity from our analysis.
Okay, thank you very much.
Okay, thank you very much.